In this second video, I wanna look at this case that I already explained to you how to set up the open channel fellow using volume of fluid method and compare it to the other case. Just again repeating here, as you see that the depth of this trapezoid, it is 200 millimeter, so each branch has a 200 millimeter depth. Okay, these two delivering water into the deeper, larger channel, which the depth of that it is 400 millimeter. So this is the case that we already talked about that, and the bottom of the channels the branching channels are not in the same level of the bigger channel. So larger cross-sectional area, and we're expecting much more water that we already saw the results in this case. Let's look at the second case. In the second case, again we have trapezoidal. This is what we have. Okay, again two branches merging together into the bigger channel, and trapezoidal. Let's look at the cross section. Here the depth is only 40 millimeter. So in this case, the depth of the branch, trapezoidal branch, is only 40 millimeter, 1/5 of the previous case. And another thing is that the bottoms for the branches are in the same level of the bigger channel. So no change in the level of the bottoms in this channel. So much more less depth into the channel and also into the water. And we want to see that when the flow developed here after merging, what's happened into the results and what we can see differently compared to the previous case. Let's see what we can see from Fluent results. This is what I showed you for the deeper water into the channels, and as you see that we have different levels for the bottom of the channels. These two branches deliver water into the big canal. So let's just review what we got. As you can see that the water, it is starting to mixing together, and the flow coming back, and it is affected the flow inside the branches. If I replay that, wavy water, that you can see that previous this is what we are seeing in this open channel when we have more depth of the water. Okay, let's compare that with the shallower water. I solved this model for the shallow water open channel flow. The model setup is same. Okay, we have volume of fluid method using here. Setup is same as before, two phases for air and water, and the phase interactions, and also the boundary conditions here for the inlet. Again, same boundary conditions we apply. As you see, I consider half of the fluid filled into the field of water at the inlet, and again 1 meter per second. So I keep the velocity constant. Two inlets. Okay, same outlets here, pressure outlet. Okay, Again, same level for the flow, for the water at the inlets and the outlet. These are open parts that on the top that we are seeing that open to air, again pressure outlet. So I keep the boundary conditions as is. I did not change it compared to the other simulation, other cases that we have, methods and other things. Everything is the same, and I already ran this for about 9,000 time steps. Let's compare the uh, compare the simulations, compare the animations to see that what's going on here. Again, this is the velocity contours at the free surface, and now remember what we had before. Okay, for this one I just play it again. You see that what we are seeing, that water here is converging together, that the delivery of these two branches coming back at the sides and affected the flow in each branch. So from from outlet toward the inlet, even getting to the inlet, that does opposite direction for the waves coming back. Now for this one it is shallow. Okay, it is only 20 millimeter the depth compared to that other one that it is we had it at 100 millimeter. So this case it is only 20 millimeter depth of the water. Let's play that. As you see that, first of all, we see here this side getting almost empty, very low depth. Interesting about the shape of and pattern of the surface wave. Let's replay that these waves converging and then diverging, and then now it is converging. Okay, and check the sides. Getting to the sides, not really coming back, a little bit around here, but it is flow stream exactly toward the direction of the flow from inlet toward the outlet. But we don't see really anything's affected the branches. What we really were interested here is this part, that after the two streams converges together, and see what's going on here. If you look at from top view, you see that here the water, the pattern of the waves are quite different compared to the uh, other cases that we have more depth into the water. And here almost as you can see, that zero, and regarding to that it is almost air, not really water. So it is like almost just wetted area of this part, but not really water there. Replay that again, and you see that this kind of waves, it is like a tidal bores that we see that when seawater sea waves getting close to the beach. This is only the free surface. Although the dimensions of the branches are not the same, this is one of the things that I have to mention compared to the other cases. So the main things that I want here to mention is the wave propagation over the surface. As you can see that here we see pattern of the converging, diverging of the flow. If I back to this one and slow it down, the replay, you see that when two water streams getting together, we see this like a this part, separation between the flow, and this is like a diverging front of the waves getting to the sides, the two sides, up and bottom, and then now converging surface waves. This is what we seeing in this shallow or less depth of the water. Okay, let me show you another case that here we also have little depth into the water, but I just extended this larger channel to see that better. What is the I'll have the disturbances after the merging of these two flow from these two branches propagate over the free surface. This is the animation from that simulation. So as you can see that here diverging of the flow, and here converging, and again a kind of diverging of the flow, again. So, and if I want to show you on the other view, you see that exactly it's like a node here, and it is like a sinusoidal waves that propagate over the, it is even like an interaction of the waves together. So this is quite different compared to what we were seeing in the flow in the channels that where we have more depth of the water. So we can see that the water depth is a very important parameters in the flow regimes into the open channel flow. So as in theory of the open channel flow, that the flow regime into the open channel depends to the and it depends to the Froude number, that it is in terms of the velocity and also depth of the water in the open channel, and we can have different regimes for subcritical or supercritical flow regime inside the open channel. Here we see that the effect of the water depth into the mixing of the flow after after mixing the flow, and how we can see that the evolving and propagation of the surface waves over the or in the bigger channel that really affected by the depth of the flow. So hopefully this video can help you to somehow to see that the similarity and dissimilarity of the uh, open channel flows that we can get from Ansys Fluent, and in this video we keep constant the flow velocity of 1 meter per second at the inlets, just using a little bit changing into the geometry regarding to the length of these branching canals, and also the bigger canal after that. But the main things that we change is the depth of the water, that in one case it is 5 times more water compared to the another case, and we see the huge difference between them regarding to the fellow reactions, fellow interactions after merging together, and also the way we see that the uh, surface waves initiated and propagated over the free surface. Hopefully this video can help you to also know that the parameters that affected the open channel flow, and how we can see that we can simulate this effect in Ansys Fluent by volume of fluid method. Thank you very much.